So following on from the previous two videos, we would use this equation here to produce this graph, and then we would use this to model this situation here. And also we've established that we need to combine the frequency. We need to define. So we need to combine the frequency along with the distance away from our target. So whenever you combine the distance away from the target with the frequency, you would need to consider the 3D version of this. So the 3D version of this would be you looking at this and then revolving it around 360 around the y-axis. So we've established that we need to consider the 3D version of this because we need to combine the distance away from the target with the frequency. Okay, so now in this video, let's try and work out the probability of us hitting, let's say within 2 to 3 meters from the target. So this is us hitting the golf ball here, and then we're going to use this to model this situation here. So when we hit the golf ball, what is the probability that we will get it within? Let's say this is 2 meters and this is 3 meters. So what is the probability of us hitting within this area here? Okay, so when we hit the golf ball, what is the probability that it will land within this region here? Okay, so it's really us going all the way down here, and then all the way down here. So this would be within 2 meters, within 2 to 3 meters. Okay, but let me just enlarge this thing here. So let's enlarge it. So that would look like this. So this here would be it's out of scale, but 2 to 3 meters. But let's instead of working with 2 to 3 meters, let's work for a general case. Let's call it R1 and R2. So for any radius, R1 and R2. Okay, so what is the probability that when we hit the golf ball, it will land within this region? Well, it landing within this region is really you evaluating this thing here. So we've got to revolve it 360 around the y-axis. Okay, so now we've got to use the cylinders. So we've got to sum up the cylinders. So it's really so the probability of it landing between R1 and R2 here is really part divided by the whole. Well, the part bit is us looking at this and working out the volume when we revolve it 360. So the parts part would be us taking the integral from R1 to R2. Okay, and so hang on, the part would be us working out this volume here, revolving it around 360. But within this part here, we need to take the integral. So it's really us taking lots of cylinders here. So let's just look at one cylinder, one thin cylinder. Hang on. Remember, we are trying to work out this whole volume here. But to work out the whole volume, we need to consider lots of cylinders. We need to sum up all the cylinders. Let's just look at one particular cylinder. The thickness associated with this one particular cylinder is dx. So we need to consider the integral from R1 to R2 of something dx, because the thickness here is dx. So we need to consider the circumference, okay, and then we've got to times it with the height. So the cylinder is really the circumference, which is 2 pi. Well, the radius for one particular cylinder would be 2 pi x, okay, and then the height would be given by the formula for this thing here. Okay, so and then the whole. So this part is the part, and then the whole. Remember, probability equals part divided by the whole. So the part is really you working out the volume of this. The whole part, the whole bit here, the whole bit would be you working out the whole. You revolving this 360 along the y-axis. Okay, so hang on. So that would be, hang on. So the probability of us getting it within R1 and R2 would be part divided by the whole. Okay, well the parts part would be hang on. So this is us trying to work out the volume of this, but we need to sum up all the cylinders. Well, the thickness associated with this one cylinder here would be dx. So that's that's this bit here. Okay, and then looking at this one particular cylinder, just looking at this one particular cylinder here, the thickness of this one particular cylinder is dx. We need to revolve it around 360. So that would be the circumference of a circle, which is 2 pi x. And then we need to times it with the height. Well, the height of this graph here is given by this. So it's really so this here is our circumference. This here is our height, and then we need to sum up everything from R1. R1 is right here. From R1 to R2. R2 is right here. So the volume for the part is given by this. Okay. So our natural. So now we need to evaluate this. Okay. So our natural instinct well, we are integrating with respect to x. So our natural instinct would to spot that this is a constant, c is a constant. So we would take 2 pi c out. But the thing is, from experience, I know that later I need to integrate it, and there's a 2 here. I'm going to leave the 2 within here, just from experience. So our natural instinct would to take 2 pi c out. But from experience, I'm going to leave the 2 in here and just take the pi and the c out. Okay. So now we need to now evaluate this. Okay. And then now integrate this. Find the antiderivative of this. That would be this. Okay. And then now it's this. Take away this. Okay, so it would be this, which is this bit here. Take away this, so that would be this bit here. Okay, and then hang on, and then let me think. And then you can see a negative and a negative. Take it out, so this will become a positive. Okay, so you've got hang on. So this is what you've got at the moment: a negative and a negative. So that makes it a positive. So notice that you've got a positive R1 here. So you've got this plus, hang on. So you've got this plus this thing here. So let's switch these two around so it looks neater, because you've got a negative here and a well, just switch these two around. Okay, so that will then give you this. So it is indeed R1 here, and then R2 is over here. Okay, so this is just a part. I will continue in the next video. We need to get the parts divided by the whole. Okay, so all that we've done is the part. Okay.